My name is Pedro Veloso, and I'm a PhD candidate at Carnegie Mellon University. Professor Ramesh Krishnamurthy is my advisor. I'm going to present the paper on Academy of Spatial Agents. The topic is interactive spatial synthesis with agent-based models. So agent-based models rely on the interaction between agents and an environment and in a simulation, and they support fine-grained interaction. Our motivation is to understand spatial synthesis as a form of open game where designers can interact with agents in a shared environment and can generate spatial configurations in real time. The challenge in this setting are related to the fact that agent-based models are typically imported from other areas and are hard to adapt or tune for custom spatial requirements. Our proposal is to develop agent-based models for spatial synthesis that can support fine-grained interaction, but also can solve spatial conflicts and can generate custom architectures. Instead of importing agents from other fields, we use reinforcement learning, a branch of machine learning, to train the agents. In reinforcement learning, in the interaction between an agent and environment, the environment provides a reward signal to the agent. So the agent can learn how to select actions to maximize future cumulative rewards. So if you embed specific goals in those reward signals, the agent can learn how to select actions and behaviors to achieve those goals. The paper focuses on prototype 1, P1, and this prototype is based on a discrete representation. So both the agents and the environment are represented in grids. So here we have a visualization of 5 agents in an environment with obstacles. And for each agent, there's a series of grids. Each of these grids has a specific aspect, specific information about the agent or the environment. And the agent can perceive the neighbors and also can perceive the environment, but can only act locally. So each agent's a space is a polynomial with no holes. So the agent can select actions inside the specific action grid, and these actions can either expand or retract the agent. And so they can combine these actions for a more sophisticated behavior. And by combining these actions, they can change their shapes and they can also move in the environment. The objectives are adjacency, area, and shape. And these objectives are parameterized, so the designer can potentially select different areas or adjacencies for each of the agents. And we combine these different objectives in a function, and uh, the difference of the gradient of that function between time steps is interpreted as the reward signal for our training. We described the learning algorithm in the paper. Here I'll briefly mention that we use double deep Q network, and we developed a custom neural network for our problem here. The prototype one was trained in a simple setting. You can see the training setup in the paper. And in this simple setup, we use 6 agents, and they're trained in randomly generated environments with random obstacles and random areas and also adjacencies and so on. And in terms of reward signal, the reward signal is based on this function that combines adjacency, area, and shape here. So after training, the model learns how to achieve those goals. So the agents know what to do to achieve those goals. But we want to test if those agents are able to generalize their knowledge to novel situations. And by novel situations, I mean situations where there are different number of agents. In this example, the agents represent a house. So there are like 12 agents. Each agent's a different space. And also new environments. We can see here A, B, and C. In the paper, we test A and C. So here in the video, you can see environment A with this irregular boundary. And besides, we also want to see if the agent is able to recover from external influence, because the goal of this prototype is not to generate an optimal layout or multiple layouts, but the goal is to interact in the future, interact with the designer and react to the external actions. So to do this, we alternate between stages where the agent selects the actions and stages where the actions are randomly selected. So we can see in the scenario A, the agent starts to populate the top of the hill, and we selected some time steps here for visualization, and we can see that the agent is able to generate good layouts, and it's also able to recover from the random actions. And this graph also shows this, so you can see that the performance for the three functions, the three objectives are good, and the agents are able to recover from the disturbances. The same thing happens from scenario C. The agent is able to occupy both sides of this stream and also the bridge. So the agent is able to sectorize, to have two sectors of this house connected by, in general, by a social space. And it also is able to perform well and to recover from random actions. In terms of conclusion, we successfully trained the agents, and the agents were able to generalize to new settings. Our parameterized objectives were also successful. We are implementing prototype 2, and we use more efficient workflows for prototype 2. The environment has variable size, so it can be changed. And we also integrated with a game engine for real-time interaction with the designer. That's it. Thanks for your attention.